A warm welcome from my side. My name is Alfred Taudes. I'm a professor here at the Vienna University of Economics and Business, and I'm also one of the CEOs of ABC Research, the Austrian Blockchain Center. One of the activities of the Austrian Blockchain Center are blockchain talks. And it's a great pleasure for me to welcome you to ABC Blockchain Talk number 23. And the topic of today's the blockchain talk is verifiability via zero-knowledge proofs. The format of the blockchain talk is always to have one speaker from an academic background and one presentation with practical applications. And in our tradition, we will have the same format also here. So the first presentation will be given by Stefan Craß, my colleague at ABC Research. He is the technical area lead, and he will give you an introduction to zero-knowledge proofs with especially applications in blockchains and in the digital product pass, which should be something like a passport that you know for people, but for products. And then it's a big pleasure for me to welcome the colleagues from Fides Innova from Canada. And they are already providing zero-knowledge proof services in a number of areas. Of course, you might ask yourself now, what is a zero-knowledge proof? In fact, it's one of the most surprising and intriguing concepts in cryptography that has the potential to transform the way that digital communication works. Because today, in today's internet, the problem is anytime you want to personalize something, you want to authenticate, you have to provide information to do that. And usually you provide too much information and you have a privacy problem. And zero-knowledge proofs are a very intelligent cryptographic device to change that. So in a zero-knowledge proof, as the name says, you can prove that, for example, you possess a password, or, for example, that in your supply chain you don't have child labor, but you don't actually reveal the information. So in a digital product pass, of course, not only your customers see your supply chain partners, but also your competitors. And it's very relevant that you keep secret which of the best suppliers you have, but you still want to prove to the other people that there's no child labor. And this, of course, is a very important concept. And I'm very glad that we have these two interesting speeches. Maybe some words about Fides Innova. As said before, they are a Canadian company having zero-knowledge proof services for practice. Today's speaker, Mel McCann, Reza Ramezan, and Mustafa Darabi. Mel McCann and Reza Ramezan, they formerly worked for Cardano Foundation. Mel McCann was the former VP of Enterprise Technology, and Reza Ramezan, the research lead. And Mustafa Darabi is the ML engineer in the project. And I'm very much looking forward to the presentation by Stefan Craß and the Fides Innova colleagues. So, Stefan, the floor is yours.
Thanks. So, welcome from my side. I'm Stefan Craß, and I'm going to present to you zero-knowledge proofs and the application in digital product passport. So first, I want to give a quick introduction about ABC Research, about Austrian Blockchain Center. So who we are a research center for blockchain and related technologies since 2019, so over 6 years now. We are independent, but we have strong ties to several Austrian research organizations, in particular the Vienna University of Economics and Business Administration, where also Alfred is teaching. We are application oriented. We are doing practical research with companies, and we are focusing on an interdisciplinary approach, not only on a technical level, but also from an economic perspective. We try to fill the gap or bridge the gap between basic research that's done on the university level and the challenges that are coming from industry and economy, doing research projects, concepts, prototype development, and also outreach activities like education and networking. So there are two parts of my talk. First, I want to give you a gentle introduction to zero knowledge proofs. They're a very complex topic, but I try to give you a high-level overview, and then I will talk a bit about the application and the digital product passport. So what is a zero knowledge proof? You can define it in different ways, but a common way to define it is that it's basically a system that uses advanced cryptographic techniques prove the correctness of a statement while preserving the confidentiality of the underlying data. So you have, at the one hand, a prover that wants to prove a claim, and on the other hand, you have a verifier that wants to check the claim and verify that it's correct. So you have these two players in this system. There's a lot of, let's say, cryptographic magic in between them. I don't want to explain all the details here, but I want to enable you to grasp the general concept. So what a verifier basically verifies the claims made by the prover, and the prover doesn't have to reveal any of the sensitive information that's underlying this claim. So only the truth of the respective claim is revealed and nothing else. That's where also the name zero knowledge comes from. So basically you learn nothing except what you need to learn, like basically the claim. This concept might seem familiar or like related to something that you might already know from the blockchain world. Like if you use a cryptographic hash function, for example, you can create a proof with that, or kind of a proof, where you can create a hash value of a document of some data set, write it into the blockchain, and then basically you can prove with that you're in possession of this document or of this data. And if in 1 year in the future somebody asks you for the data, you can send it to them and they can verify that it has the same hash as 1 year ago. So that's kind of a data certification or notarization on the blockchain. And this we can already do with cryptography, but zero knowledge proofs go a lot further than that. So one step further at least, because you can prove anything with them. They're like a general purpose framework, and you can they allow for general purpose programmable privacy. And how this can work, I will try to tell you in the next few minutes. So a simple classical example for zero knowledge proofs is always this kind of identity checks at a club, for example. You want to prove that you're over 18 years old or over 21, depending on the country you're from. And but you don't want to reveal your ID, because the ID shows how old you are, it shows your name, and you're not comfortable with sharing that with a random person. So what you can do here is to create the zero knowledge proof. So the zero knowledge proof uses some private information that's encoded in your ID document and transforms it into a zero knowledge proof that basically proves some claims. And these claims include that you have a valid ID document first, that this valid ID document is signed by a trusted authority, like the Austrian police, for example, and most importantly, that this ID document has a field called birth date, for example, that is has a value that's more than 18 years ago. So basically it demonstrates to the verifier, like the security man here, that you are at least 18 years old, and that's all what he needs to know. From a technical perspective, how do these zero knowledge proofs work? Like also, again, I want to give you a high level abstraction. On the upper left corner, you see a claim that's kind of a formal statement. That's just an example. You have x squared plus y equals z. And then you have a prover that wants to prove something with the statement that says, okay, I have c equals 6. So that's the public part of the claim where of the statement where you say, okay, that's an instance of the claim. I say c equals 6, and I know like values x and y that satisfy this equation. Of course, it's like a trivial example, but just for the sake of simplicity, that's something that could be used as a zero knowledge proof. So the prover wants to prove that this claim is valid for c equals 6. The verifier is curious to learn that it's valid, so he wants to verify the proof. And what the ZKP system does, so basically the cryptographic algorithms behind this approach, they generate based on the claim, based on the public statements, and based on the private information that comes from the prover, a proof. And this proof can then be verified by the verifier, also using some other formal process with cryptographic algorithms. So that's the general idea, the general workflow behind the zero knowledge proofs. More from a technical perspective, from an architecture perspective, you have in the middle of the zero knowledge proof, there's a program, like also called a circuit, where you encode all the constraints that you want to check. And you have two types of input then. You have the private input, the things that you don't want to disclose but are necessary to prove the claims. And you have the public input. These are those parts that you want to share with the verifier. And using this program, the inputs, the private inputs, the public inputs, the ZKP system can create a proof that can be then checked by the verifier. And there's an important subclass of ZKPs that is called non-interactive ZKPs. That basically means that the verifier doesn't have to contact the prover to check for the correctness of the ZKP. You just need to analyze the proof that was sent to you by the verifier, by the prover, for example. There are a lot of different ZKP systems. ZKP is not one single technology. There are a lot of different cryptographic methods involved and different properties like for performance and security. But some of the more famous ones are ZK snarks, ZK starks, or bulletproofs, for example. And these are all technologies that are currently used in practice. The main challenge when using zero knowledge proofs is that the computational costs for generating a proof, but also for verifying a proof, are still relatively high, but these are getting better and better every year. So in the past, generating a proof could take several minutes and verifying several seconds, but now we can generate proofs below a second and verify in milliseconds, basically. So now we are basically crossing the threshold where they become practically useful. Yeah, we're having like this Austrian blockchain talk. So the question is, what do zero knowledge proofs have to do with blockchain? And the short answer is they are not depending on each other. So you can have zero knowledge proofs without blockchain. You can, of course, have blockchain without zero knowledge proof, but there are very strong synergies between these two technologies. In particular, zero knowledge proofs are able to solve the privacy dilemma of blockchain. What's that? Basically, if I want to share sensitive data, I have always the problem that if I do it on chain, then everybody can see it. It's fully transparent for until the end of times. But I don't want to share my birth date, for example, on a blockchain. So if I want to prove my age, I can do it using zero knowledge proofs, and that's a useful approach. So basically, using blockchain, I can define a zero knowledge proof that shares only the information that's absolutely necessary for a smart contract to function, for example, I can create this proof off-chain, so I don't have basically leak the private information on the blockchain. And then I send the proof to a smart contract, put it on chain, and the smart contract can then internally verify the correctness of the zero knowledge proof and trigger certain actions based on the smart contract logic. For example, if you're over 18, then I send you a token. What kind of use cases do zero knowledge proofs support? The most famous one, or the one that was like the first big use case, are privacy preserving cryptocurrencies like Zcash, for example, or later Monero. So this exists since 2016, so almost 10 years now. And the idea here is that you can have shielded transactions that hide the sender, the recipient, and the transaction amount of a cryptocurrency transaction, while still allowing the system to verify that the sender has the necessary coins. So you cannot just invent coins out of thin air. You have to show that you have received them first. And in contrast to Bitcoin, you cannot say anything about the transactions. Okay, in Bitcoin, you still have the pseudonymity, so you still can hide behind your Bitcoin address. But in the end, there's always the possibility to correlate different transactions. And at one point, you might be able to find out who the participants in the transactions were. And this is what privacy preserving cryptocurrencies prevent. Another use case related to blockchain are ZK rollups. They are not enable layer 2 solutions for blockchains that enable cheaper and faster transactions. How do they work? Basically, you execute transactions separately from the main blockchain like Ethereum, and only periodically you create a zero knowledge proof that combines the executions of many transactions and basically proves that they were executed correctly. And only this information you write to the main chain. And with that zero knowledge proof, you protect the integrity of all of these other transactions without needing to put all the transactions directly on the main chain. Then identity verification, we already mentioned, like the age check on the beginning. You can use that for your customer processes, for example, in banks. And then you don't have to share your identity documents. And finally, also rental applications might be made easier with zero knowledge proofs. If you want to prove to your landlord that you have sufficient funds, sufficient income to rent an apartment, but you don't want to tell them how much you earn exactly, you can create a zero knowledge proof based on your bank statement that verifies that you have more than X euro income per month. So now heading over to the supply chain management part. These are preliminary results from a project called PASSAT, Digital Product Passport Austria and Beyond. That is a project, a joint project with Austrian and German partners, with company partners and also research organizations that are working on digital product passports. First, I want to give a quick motivation why zero knowledge proofs could be useful in supply chains. First, in supply chains, transparency becomes very important also because of new EU regulations. There's the Eco Design for Sustainable Products Regulation. There's the Corporate Sustainability Due Diligence Directive and a few others. So basically the regulators want more transparency. Also the consumer wants more transparency because, for example, they want to learn more about a product's ecological impact. So it's in the best interest of companies to share this kind of information. But on the other side, they often are not willing to share this information because it might be some secrets. So they only want to share what's absolutely necessary and not more. And ZKPs enable to balance this trade-off between the transparency on the one hand side and the confidentiality and privacy on the other hand. So you could, for example, prove the compliance with certain emission regulations and standards, but you don't have to disclose the details of your process and your detailed emission profile, for example, for each production stage. And it can also be combined with smart contracts to enable decentralized automatization, because the supply chain actors can prove that they fulfill certain constraints that are necessary for a smart contract without disclosing the underlying raw data. And then I can trigger follow-up actions, for example, trigger some payment. What do we do in the Passat project? We create a digital product passport. We are working on a general solution for digital product passports that are interoperable and that store valuable information about specific products. And these DPPs will be required in the EU for certain product groups in the upcoming years. And they can be useful both for the customer, but also for other stakeholders in the supply chain, like repairers or recyclers, and they can all read the information about the product. And what we are doing as Austrian Blockchain Center and this project is we follow two directions. First, we try to protect the integrity of the DPP, so prevent manipulations by notarizing the DPP on the blockchain using data anchoring. So basically, we create a hash of the DPP, and then we store the hash value on the blockchain, which means nobody can retroactively manipulate this DPP, and there's no possibility of forging the information there. On the other hand, we look into options how to include zero-knowledge proofs, as mentioned before, into the DPP, so to enable the producers to share certain information based on underlying data that they don't want to share. Yeah, what are examples of use cases that we are looking into in relation to the DPP? First, we want to check that the product has ethically sourced raw materials, so that they are not coming from some war zones, for example, or that they were sustainable, they have a sustainable source. There's no human rights violations and so on. So basically, but we don't want to disclose where we got them from, because that might be interesting for our competitors. Secondly, as I mentioned before already, we might want to show that we meet the carbon footprint requirement, but I don't want to give the details how many tons of CO2 exactly each production step took. I could also think about ZKPs related to recycling. So I want to show how much percentage of my product is made of recycled parts, but I don't want to tell which parts are recycled. I want to show that my product is regulatory compliant, but for example, with regards to banned substances, but I don't want to give any details. If I want to resell a product, for example, a battery, I want to know how it was used, if this usage is compliant with my resale criteria, for example, that it was not recharged more than 1,000 times, but I don't want to track the user exactly and learn some details about how they use the product. And last but not least, we can also envision a zero-knowledge proof where we say, okay, this product was made in a specific region, for example, made in Europe, but I don't want to tell where my factories are exactly. So these are all kind of examples that we are looking into in this project. And one example that I can give you more details about is material composition. As an example, we took the textile sector because we have some partners from there, but in theory, it could work for any industry. And the idea is that the producers might want to partially share the materials used in their products, but not the complete composition, because this might be a trade secret. So how do you do that? You encode the constraints of your claim in a zero-knowledge proof circuit. And this circuit might have these three constraints. So first, the producer has a complete list of materials that have a specific hash X. Then we check that the material shares add up to 100%. So I'm sure that nothing is missing. And what I actually want to prove is that the product contains less than Y% of elastane, for example. I mean, that might not be a problem that's occurring in practice, but just as an example, this is something that could be programmed. Okay, now we have the zero knowledge proof, but this proof just says that the producer has like this list of materials, but it doesn't say yet that this list is authentic or correct. So what we can do to add trust to this ZKP is that we first anchor this material hash X to the blockchain. So that prevents that the producer can change the materials later. And also we let an auditor, a third party, confirm this material. So if somebody does a chemical analysis, for example, on this product and they say, okay, that's correct, this composition, then they can also confirm it on the blockchain and this can add trust to the ZKP so that it cannot be manipulated. How could this example look like? We have like a private input that says maybe 16% elastane, 35% polyester, 49% cotton. This is the information that the producer does not want to share. What the producer wants to share is the public input that says, okay, 20% is the threshold. That's the maximum amount of elastane that I want to prove. And I share also the hash value X. Based on that, the ZKP system can generate a proof that says I have a product with the material hash X that contains a maximum of 20% of elastane. And the verifier can then simply check this proof using these algorithms from the zero knowledge proof system. And in addition to that, they can also check the on-chain entry that includes the hash and the auditor confirmation. And based on this information, they can be sure, yes, this information or this zero knowledge proof holds and it is correct according to the statement that was included with the proof. So the product has maximum 20% elastane, and that's what I want to know, and I don't need to know more. We are currently building a tool based on these examples. Don't want to go too much into details because it's still work in progress, but on the bottom, you can see how such a proof looks like. So it's not much more than a list of numbers. It continues a bit after that, so it's not much bigger than what you see on your screen. So it's less than 1 kilobyte using this ZK snacks, for example. Yeah. To conclude, how can we achieve verifiability with zero knowledge proof? Basically, zero knowledge proofs enable you to publish a verifiable statement without having to disclose the underlying private data. They are a complementary technology to blockchain that can help to balance transparency and privacy constraints there. And specifically for supply chain applications like the DPP, as we're seeing in the Passat project, such applications can benefit from zero knowledge proofs by enabling companies to share exactly what they need to share, but nothing more. So ZKPs are still a new technology, and there are many exciting developments at the moment. But yeah, the future still lies ahead, and we are very interested in seeing how it will develop. Thanks, and I'm looking forward for your questions.
Thank you very much. My name is Mel McCann. I'm the Chief Strategy Officer and co-founder of Fides Innova Labs. And myself and the team today are going to talk a bit about what we do, how we leverage zero knowledge proofs, or specifically function hiding zero knowledge proofs to achieve verifiable computing. The gentlemen are calling in from all around the world. I'm from Ireland. Mustafa's in Germany, Rez and Hamid are in Canada, and Mo is in Dubai at the moment. So we're quite decentralized to start. Next slide, Reza, please. So for this presentation, we would like to cover the following: introduction into function hiding zero knowledge proofs and verified computation, the theory behind that, how you integrate it, the tools that you can use, and then a little bit about us, and then the joint Q&A with Stefan. Next slide, please, Reza. So verifiable computing is a cryptographic approach that allows a client to outsource computation to an untrusted server and later verify quickly and efficiently that the server performed the computation correctly without re-executing this. At the core of this is a mathematical model of a program that then produces a function hiding zero knowledge proof. This allows us to prove the function of the program, but without giving away any of the details. So as Stefan mentioned, zero knowledge is given away, but you can still prove something. From this approach, there are three distinct outcomes. There is verified computation, so knowing that your system is running as intended. There's the security element of it. For example, and we do it at the firmware level, but you can do it at different levels. Knowing that, let's say, malware has not been injected into your firmware. And then there's an assurance part to this. So Stefan gave an example of the supply chain, and I'll give another example later to talk about assurance and why that's applicable to this. Next slide, Reza, please. So for us, myself and the gentleman, this journey started about 1.5 to 2 years ago, where we started looking into research topics that were new to the blockchain industry. As mentioned, my background is in blockchain, and also my colleague Reza came from the Cardano Foundation. Once we left there, we started researching function hiding zero knowledge proofs and looking into the applications of that. We started with IoT systems because they were the natural sort of low-hanging fruit, sensors, smart buildings, and that type of thing. So I'm going to give a few examples during this, so it provides people context. At the time, DPIN was kind of hot, and people were connecting a lot of devices to blockchain. But they were, the problem that we noticed essentially was that there was implied trust. People were trusting all of these devices, but without proving that they were functioning as intended. From there, we started expanding and looking at the use cases, looking into how we can apply this to cloud computing, and moving the trust anchor away from the cloud, which you have to trust for the execution of your program. Let's say it's in a sensitive program, and being able to verify that it was executed as you wanted it to be. And then following that, we started looking into machine learning. And in the machine learning space, like a lot of companies are spending millions of dollars on training AI models that they want to license to customers without having the customers, being able to steal the model weights or the architecture. So if we think about an insurance company that uses a third-party AI for risk scoring, the AI provider, can prove that they ran a specific model because you can prove the entire function on the user's data without ever revealing the weights, the model's weights to the insurance company. So just for food for thought, being able to prove an entire program, and we do this in many cases at the opcode level of a processor. We assume no trusted environment, no TEEs or secure enclaves. And we wanted to go to that level as a company that's essentially focusing on trust. So a few years ago, there was a scandal in the automotive industry, let's say, about a company that was fudging their emissions. If they had to publish a commitment prior to, they would not have been able to change the software, and they wouldn't have been able to get away with that. So I think that as we've progressed over the last few years, we look around and see more and more and more applications of where this can be applied. If you think police cameras, because there's a lot of deep fakes happening. If you're thinking of chain of custody or an airplane black box, these are all very, very appropriate examples on how to leverage this technology, being able to prove that something executed as intended. Next slide, Reza, please. So part of this, the process of actually doing verifiable computing, let's say, is one, the setup and the commitment, which can be done by, let's say, a manufacturer. And my colleague Reza will go into this in a lot more detail. The next step is the publishing of proofs. And then the final step is verification. So these all combine into allowing you to, in advance, publish a commitment, verify it. And for this, we don't have to use blockchain. Stefan mentioned a very good point in that zero knowledge proofs and blockchain are quite complementary, but they can function independently. So we do use blockchain because it's appropriate for many of the use cases. If you think about regulators, or the fact that no information is given away. But if you have another scenario, let's say the new class of BMW cars, where they have the different superbrains, the different superbrains will be able to prove to one that they are functioning as intended. And these proofs are streamed in as the processor is running. It's not like typically in cars, a check is done at the start and then that's it. Next slide, please, Reza. So over the past few years, we've looked at this technology and we refer to it as a platform because we not only have SDKs in multiple languages, but we have an AI agent and an LLM to make this technology more accessible. We have a custom version of Ethereum with custom nodes that allow you to react to the data and proofs that you send. You don't just have to send the proofs on their own. You can forward other useful information that you might want to know. And these nodes include scripting capabilities and machine learning capabilities. And on top of that, we have admin portals, user portals, and mobile apps. So we've built an entire platform to support this technology and make it available to the public. And now I would like to hand over to my colleague Reza, who will dive into the theory behind verifiable computing.
Thank you very much, Mel. Hello, everyone. My name is Reza, and I'm going to mainly, for the rest of this presentation, cover 3 items with my other colleagues. The first part, which is reviewing some theories about verifiable computing, will be covered by me. Then Mustafa will discuss about integration, and Mo will show you some how to utilize our tools for the third part. For the first part, I want to quickly review about the verifiable computing and also zero knowledge proof. In these scenarios, we have 2 main roles, prover and verifier. In ZKP scenario, prover is going to show that or guarantee that it owns a piece of knowledge, like a secret or something, and verifier's job is only verifying this claim. In verifiable computing, as I showed here, the prover has a computation, and verifier's job is the same. He's going to verify whether the computation is executed correctly or not. ZKP, we can say it is formalized in 1985 by 3 professors, Professor Shafi Goldwasser, Professor Micali, Silvio Micali, and Professor Charles Rakoff, through their papers, which is called The Knowledge Complexity of Interactive Proof System. But verifiable computing, which is the main focus of our work, is formalized in 2010, mainly through the work that Genario, Genti, and Pamo they did, and they published a paper with the title of a non-interactive verifiable computing. outsourcing computation to untrusted workers. And in the general form, or the classic form of verifiable computing, we didn't have ZKP or other similar to ZKP scheme at the beginning. Mainly the proposed method was based on some IOP, non-interactive proof, but what we define in this area, actually Fides define, is this one. In our framework for verifiable computing, we are mainly using ZKP and functional commitment scheme, two main components. Functional commitment scheme, this component ensures that the prover cannot change the code or input after the commitment, and ZKP part mainly discuss about the correct execution while preserving the privacy. If I want to go deeper, as I said, the modern verifiable computing does not require functional commitment, or its ZKP is in modern form, but we in Fides framework we use these two components, and this is our definition for verifiable computing. In fact, using functional commitment, which is which cryptographically bind the prover to a fixed function or input, we are going to ensure that the prover cannot change the code or the program. For the ZKP part, Stefan provided a very good introduction about ZKP. Here we use ZKP in our verifiable computing scheme, and mainly to verify the correct execution while preserving the privacy. If I want to say in simple word, for functional commitment, it answers which exact function were you forced to compute. And if we don't have this in our framework, and that's the reason we put it in our framework, is the prover is not cryptographically bound to a specific function. For the ZKP part, we are going to answer, did the commitment function evaluate correctly on a commitment input or not? And without ZKP, we are bound to a function, but we cannot prove that the computation was executed correctly. And now I'm going to review a little bit more in detail, review function commitment schemes with a little bit more details. Stefan discussed about the ZKP. That's why I don't want to review ZKP anymore, and I'm going to focus more on function commitment schemes. Usually, if you look at the papers, when people use function commitment, mainly they refer to input hiding functional commitment, or IHFC. What is input hiding functional commitment? In this scheme, we have again two roles, prover and verifier, and we have two main elements, function f and input x. Function f is known for both parties, prover and verifier, but input x is secret and is known only for prover. And now the prover provides a commitment to input x, and later is going to provide a proof and output y to show that the y is equal f over x, or the function is executed on secret input x, and the verifier's job here is only to verify this claim, whether this claim is correct or not. And this is the main functionality for functional commitment schemes. But there is another class of algorithms in this area called function hiding functional commitment. Again, look at the same scenario. We have prover and we have verifier, and we have the same elements, a public function a function f and input x. In this scenario, this time function is hidden. Function is with prover and the input x is public. This time, the prover create a commitment to function, not the input x, because the function is hidden. Later, the prover provide a proof to show that the computation is done correctly and the output is y. Verifier's job here is to verify this claim and whether this function, which is unknown to verifier, is calculated over x correctly or not. When we try to write the algorithm, create our SDK and our tools, mainly we were focused on this job from Professor Dan Boneh, Stanford University. This paper, Efficient Functional Commitment, How to Commit to a Private Function, which is published in 2021. But gradually, due to the performance, we changed the algorithms, use the modern and advanced lookup table methods like lasso jolt, and we came up with our own scheme. And if you are interested to learn about our cryptography scheme, you can go to our GitHub, which is a ZK IoT Verifiable Computing. Go to the wiki page here, and here we provided all the mathematics and all the 4 steps for set up the system, create a commitment, proof, generate a proof, and do the verification. So as I mentioned, our verifiable computing framework is built up based on ZKP and function hiding functional commitment scheme, combination of these two. The provided or the developed SDK covers 4 steps: setup, commitment, proof generation, and verification. Commitment is done only one time during a computation lifetime or a software lifetime. And it creates a commitment that shows or demonstrates the computation before execution trace or before executing the program. The third part, proof generation, is done several times or every time that someone needs a proof about the execution of the program. And the generated proof can be stored anywhere, like a blockchain. In our case, our proof can be stored on our blockchain, but it's not necessary. The only elements which should be stored on an immutable database, a blockchain, is the commitment part. Last but not least, we go to the verification. Anyone on the internet can get a copy of the commitment from the blockchain and a piece of proof, and using these 2 elements can do the verification part. You can see the generated code and the tools and SDK through our GitHub at this address, ZK IoT Verifiable Computing. But the next challenge was, after creating these tools, is how to integrate these tools, the tools that is developed based on these 4 parts, with an arbitrary code. Assume we have a C++ code, assume we have a assembly code, and now we have an algorithm. It does the verifiable computing at some given performance and level. And now this question is how we can bring it and add these tools to the and to an arbitrary program. And that's why we defined two main methods. And my colleague Mustafa is going to cover this part and discuss with you how we are going to use develop SDK based on these four steps for verifiable computing algorithms into the program. Mustafa, please continue.
Thanks, Azza. Hi, everyone. I'm Mustafa Darabi. I'm ML engineer at Fides Innova. In the second part of this presentation, I'm going to walk you through how to integrate verifiable computing algorithm into arbitrary code. And usually we consider a code on C++ to do that. Please go to next slide. So we propose two methods, embedded ZKP and assisted trigger. In embedded ZKP, this approach itself generates the execution trace, and by injecting two parts of the verifiable computing code, it can generate the zero knowledge proof. And in assisted trigger, the program initiates a trigger for a Fides Innova tools to generate the execution trace, and it uses Fides Innova proof generator to create the ZKP and give it to verifier to verify if the code is executed as intended. Please go. Yeah. So in this slide, I'm gonna compare these two approach. So embedded ZKP is it is usually we run it on an actual CPU, but for assisted trigger we use the GDB debugger in addition to CPU. And embedded ZKP generates the proof implicitly. However, for assisted trigger, we need another tool like what I will discuss. We need Fides Innova tool to provide the proof. And for the workflow, they are very similar to each other, but there is a bit of difference between these two workflow. But I will explain in more details these two workflow in the next two slides. But if I want to say it in a big picture, first we compile it and produce a commitment, and then we produce a binary executable file from the commitment to generate the proof. And then at the end, we give the commitment and proof to verifier to verify the execution of the code. I will explain it in more details in the next two slides. And for the proof generation, it is automatically generated in the embedded ZKP. But for assisted trigger, developer needs to manually run the proof generator. And for use cases, embedded ZKP is suggested to be adopted in production development. However, assisted trigger is very good for fast deployment, and it is very good for the research development. And for advantage, embedded ZKP has a lower computational complexity. However, assisted trigger is very straightforward for developer to use it, but it has a bit more computational complexity and it's a bit lengthier if you want to apply it, but it is more straightforward. Please go to the next slide. So in this slide, I'm gonna explain in more detail about the embedded ZKP. So we have a program.cpp in C++ that we want to generate the verification for that. And in this approach, we inject two verifiable computing code using the Fides Innova library with name of Fides Innova.h. We inject this code, this block of code, and give it to GCC compiler, and it gives us the assembly version of the program. And by using the Fides commitment generator and also add the second block of the code to the program, and compile it, we can produce a binary executable version of the commitment. And if we give it to the CPU, we can achieve the proof. And then we give the commitment, which is generated previously via Fides commitment generator. We give two of the proof and commitment to the verifier. And then at the end, we can verify if the code is executed as intended. So please, next slide. So in the second approach, the assisted trigger, we do not inject the code and we do not use the library of the Fides Innova. In this case, we just first compile it via GCC compiler and produce the assembly version of the code. And then using the Fides commitment generator, we can produce the commitment. But here we after commitment, again, similar to the previous approach, we you compile it and produce a binary executable code. The difference here is the Fides tools that we use it here for the proof generation. And then again, like the previous one, we compare the commitment and proof in verifier to verify if the code is done correctly. This next slide. So I want in this slide to like show the workflow in more details. So for embedded ZKP, we the input is program.cpp, and also, as I mentioned, we need to inject code, the Fides Innova SDK. We compile it, it gives us a program.s in assembly. And because our implementation is for IoT devices, here we need to update the device config.json based on the device that we're gonna provide the verification and proof for that. So we update the device config and make it specific for our device and give it to the Fides Innova commitment generator. And then it gives us the commitment. And we compile the commitment and make an executable binary version of that and give it to the proof generator and gives us the proof. And then at the end, we compare the proof and commitment, and we can verify if the code is run correctly. For the second approach, assisted trigger, as you can see, we do not inject any code at the beginning. We just first compile it and gives us the assembly version of the code. But here again, we need to update the device config.json based on the specification of the device that we are working with. And we give this program.s and the updated device config to the commitment generator, and it will provide us with the commitment. We compile it, we make a binary executable version of that, and give it to the proof generator, and then it gives us the proof.json. And we compare the proof.json with commitment.json at the verifier at the end, and we can verify if the code is run correctly. So in the third part, my colleague Mo will show you the real implementation of the code, and I would like to pass it to Mo. Thanks a lot.
Thank you, Mustafa. Hello, everyone. Just let me to share my screen. Okay. In this part, I'm going to show you how to use the Fides Innova Zero Knowledge Proof. Here you can see my terminal and also our GitHub repository. First, we need to use a C++ code file, and we've already provided one in this repository, as you can see. Now, we need to generate an assembly file and an executable binary file for this code. To do that, we are using the G++ compiler. Now, I first run the G++ to generate the assembly file, and sudo to generate the executable file. We run the G++ once again. Okay. Here we can see that we generated the assembly file and the executable file. Now, for the next part, we are going to use the Fides Innova tools to generate the commitment and proof. For the commitment file, we run Fides Innova-C, and then we add the sample.s, our assembly file, to it. Then we will hit enter. And for generating the proof file, we use Fides Innova-P for proof. And we provide it with the executable file called sample. Okay. As you can see here, now there are two files generated, sample.prf for proof and sample.com for commitment. Finally, to verify them, we can run Fides Innova-v and sample.com for commitment and sample.prf for proof. If the verification is correct, you will see accept in the terminal. Thank you for your attention. Mel, can you continue? You can continue now.
Let me share my screen again for Mel.
Thank you very much. Oh, you want to go ahead, Reza? Sorry.
I just wanted to add something here. What Mo showed you here, actually, we have it on our YouTube through this video. Later, we will share this presentation, and you can go to this link, and you can see all those 3 steps that Mo explained: generate a commitment, generate a proof, and verify the proof. Keep in your mind that in this example, we didn't use a blockchain. We just wanted to show how tools can create a commitment, a proof, and verify the proof. But in practice, after creating a commitment, you have to upload it on a blockchain, because nobody should be able to change the commitment later. And this is a critical component for the verification part. Okay, so that's why we need a blockchain to keep a record of this commitment. So yes, sorry, Mel, please.
Yeah, thanks, Reza. So in that vein, before we wrap up, I just want to go back to what I mentioned before, which was supply chain assurance. So if we think about an automotive manufacturer who has suppliers of lots of different components, let's say for their infotainment system, those suppliers can publish the commitments a year and a half before the components are actually put into the car and go live. And what that tells the manufacturer, the automotive manufacturer, and the component manufacturer, once the proofs start streaming from those devices, they will know that there has been no tampering of the components during that supply chain. So I wanted to just revisit that while you have a bit more context after listening to the gentleman talk about how you generate a commitment, how you generate proofs, and then the verification of that. I hope that now, after meeting the Fides team and also getting an idea of what we do and how we do verifiable computing, you found it informative. It sparked some ideas on how you can apply this to your own lives. If you're interested in verifiable computing and Fides Innova Labs, please connect with us on the links that Reza had in the previous slide. We do provide free software licenses for academic institutions, and for all other purposes, businesses big and small, we have a tiered approach to that. So on behalf of myself and the Fides Innova Labs team, I would like to say a big thank you to the Austrian Blockchain Center for hosting us, and thank you to the audience for joining us today. So thank you.
Yeah, thank you very much, Mel, and all your colleagues from Fides Innova. It was a very interesting presentation, and I'm really fascinated on what can be done now in this field. And I think it really solves very critical issues, because a lot of the things that you hear about fraud and tampering, they really now can be dealt with. And if new technologies would be applied in more depth, and I hope we also can contribute that by making them known to the Austrian community. So once again, thank you very much.